I mean, for generations, the medical consensus around the human body, it relied almost entirely on this, like, mechanical breakdown model.
Hmm.
The prevailing thought was basically that biological life is governed by the exact same laws of physics as a combustion engine.
Right. Yeah.
You know, you put miles on the chassis, the brake pads wear down, the belts get brittle, and eventually the system just sort of succumbs to inevitable wear and tear.
And that mechanical analogy was incredibly sticky, right? Because it perfectly aligns with our everyday experience of the physical world. I mean, if a piece of machinery is used continuously, friction and oxidation degrade it. So naturally, we assume the biological machine was failing under those exact same principles of cumulative damage.
But poring over this massive stack of longevity research from 2026, it is strikingly clear that the mechanics manual has just been thrown out entirely.
Oh, absolutely. It's completely obsolete.
We are looking at a biological landscape that fundamentally rejects the idea that aging is just this passive degradation. And that brings us directly to you, the listener. Welcome to today's custom-tailored deep dive into the source material you provided us.
Yeah, we've got a great one today.
We really do. We know your specific parameters, by the way. You are 34 years old, a father of two, standing 5'11" and weighing in at roughly 85 kilos. And your objective here isn't to, join the ranks of those eccentric billionaires trying to achieve immortality or upload your consciousness to the cloud.
Which is probably a healthy mindset.
Right. You have a highly practical, immediate mission. You just want the biological architecture to maintain your current 30-something energy well into your 60s, specifically so you can hike, camp, and keep pace with your kids without feeling completely wrecked.
And honestly, that is a completely viable objective based on the current literature. The scientific community right now is heavily focused on extending what we call health span.
Health span, right? Not just lifespan.
Exactly. It's about compressing that period of morbidity, sickness, into a tiny fraction at the very end of your life, rather than just extending chronological age while you're bedridden. The data strongly suggests that maintaining high functional capacity into your 7th decade is largely a matter of managing cellular communication.
So our goal today is to decode this cutting-edge science and synthesize a realistic, physiologically sound roadmap for your life. Because the sources indicate 2026 is a real watershed moment for longevity.
Oh, the breakthroughs this year alone are staggering.
Yeah, we're moving way past theoretical mouse models and into active human trials. So we're going to explore the mechanics of epigenetic reprogramming, look at the pharmacology, clearing out cellular debris, and ultimately map out how a video game console and a telescope actively influence your endocrine system.
That last part is so crucial for his specific lifestyle.
Definitely. But let's start by dissecting the actual mechanism of aging. If we're abandoning that wear and tear model, what is actually happening at the cellular level?
Well, the current consensus centers on 12 distinct hallmarks of aging, but the primary driver, like the apex mechanism, is epigenetic alteration.
Okay, break that down for us.
So think of it this way. Your DNA is the fixed hardware, right? It's the static code. The epigenome is the operating system. It consists of these chemical modifications, primarily DNA methylation and histone modifications, that basically dictate which genes are turned on or off in any given cell.
So a liver cell and a neuron have the exact same DNA, but they're just running different software programs.
You nailed it. That's exactly it.
So aging, then, is essentially a loss of epigenetic information. The code hasn't degraded, but the chemical tags instructing the cell on how to read the code, they get scattered.
Right.
It's like the body cells don't actually forget how to be young. It's more like the software is still there, but the body just lost the password to access it.
That is a perfect analogy. The operating system gets corrupted, and cells literally lose their identity. They just forget what they're supposed to be doing. And when a cell accumulates enough of this epigenetic noise or sustains severe DNA damage, it enters the state called senescence.
Right, senescence. I saw this a lot in research.
It permanently halts its cell cycle. Historically, we thought this was just a protective anti-cancer mechanism, like stopping a damaged cell from multiplying. But the pathology of senescent cells is actually much darker.
Because they become what the literature commonly refers to as zombie cells, right?
Yes. They refuse to undergo apoptosis, which is programmed cell death.
They just sit there.
They just linger in the tissue. And worse, they begin oozing this toxic cocktail of inflammatory proteins, cytokines, and proteases. We call it the SASP, or senescence-associated secretory phenotype.
So they aren't just dead weight, they're actively harming the neighborhood.
Exactly. This localized secretion drives systemic inflammation and actually induces senescence in the neighboring healthy cells. It is a biological chain reaction that degrades tissue function globally.
Wow. Okay, so the million-dollar question, based on the research stacking up on my desk here, is how the scientific community is attacking this. And the literature seems to divide the strategy into two main prongs: reprogramming the corrupted code and chemically clearing out the senescent trash.
Right.
Let's look at the reprogramming first. I mean, I want to cut through the hype here because we hear about billionaires trying to live forever, but what is actually working in labs right now? I'm seeing endless references to Yamanaka factors.
Yeah, the Yamanaka factors are huge. Shinya Yamanaka demonstrated that by introducing four specific transcription factors, OCT4, SOX2, KLF4, and CMYC, you can essentially hit a partial reset button. You force an adult cell to erase its epigenetic memory and revert back to a pluripotent stem cell.
But doing that in a living human sounds risky.
It is. The problem with full reprogramming in vivo is that uncontrolled stem cell proliferation leads to teratomas.
Massive tumors.
Exactly. So the breakthrough we are seeing now in 2026 is partial reprogramming.
Pulsing the factors.
Yeah.
Like applying them just long enough to clear the epigenetic noise and restore youthful methylation patterns, but withdrawing them before the cell completely loses its somatic identity.
Precisely. You reset the methylation clock without turning the cell into a total blank slate. And this isn't just theoretical anymore. This is happening.
Right, the FDA milestone.
Yes. The FDA recently cleared the first human trial of this technology through Life Biosciences. It's based on David Sinclair's laboratory research. They're using this experimental drug designated ER100 to treat age-related vision loss.
Which is incredible.
It really is. By delivering a combination of three of those factors via a viral vector, they've actually demonstrated the ability to restore youthful gene expression in retinal ganglion cells. It allows damaged optic nerves to literally regenerate.
Which was previously thought impossible in adult mammals.
Completely impossible, until now.
That is a staggering biological mechanism. And, speaking of shifting genetic expressions, the source material also highlights some wild cross-species gene transfers, like that May 2026 experiment with the naked mole rat.
Oh, the University of Rochester study. The naked mole rat is such an anomaly. It lives 10 times longer than similarly sized rodents, and it exhibits near total immunity to cancer.
10 times longer.
Yeah. And the researchers isolated the gene responsible for producing high molecular weight hyaluronic acid, which is this complex sugar that surrounds their cells in a dense protective matrix, and they successfully transferred it into normal mice.
And what happened?
The result was a dramatic reduction in tumor incidence and a massive extension of their median lifespan.
Wow. And then you add that to the Turritopsis dohrnii, right? That tiny jellyfish capable of transdifferentiation.
Yeah, the immortal jellyfish.
When it's injured or starving, it can repeatedly revert its adult cells back into polyps, basically hitting a biological reset button. But, I have to play the skeptic here for our listener.
Fair enough.
We are not rodents, and we certainly aren't jellyfish. Transferring longevity genes into a mouse is fascinating. But how does this translate to a 34-year-old dad who's just dealing with, joint pain from picking up his kids right now?
Well, the cross-species studies basically just prove the biological plasticity of aging, but you're correct, we aren't splicing jellyfish DNA into humans quite yet. This is where the second prong of the strategy comes in. Clearing the trash using senolytics and repurposed drugs.
Okay, so clearing out the zombie cells we talked about.
Exactly. Instead of trying to reprogram the epigenome, we use molecules that selectively induce apoptosis in those senescent cells. ABT-263 is prominently featured in these papers.
Yeah, I saw that. It's a topical drug, right? Originally developed for oncology.
Originally, yes. It's a BCL2 inhibitor. Senescent cells rely on this BCL2 family of proteins to basically survive their own toxic internal environment. ABT-263 temporarily blocks those survival proteins, pushing the zombie cells over the edge into death.
Good riddance.
Right. And then the local tissue is free to regenerate using healthy cells. We are seeing topical applications of this drastically improve the strength and wound healing capacity of older skin, literally making it heal like kid skin.
That's wild. But what about pills? The systemic pharmacology seems even more aggressive in the research, like the TAME trial.
Ah, yes. targeting aging with metformin. They're trying to reclassify aging as a treatable indication. Metformin activates AMPK, which is an enzyme that acts as a cellular nutrient sensor. It basically tricks the body into a state of mild energetic stress to trigger repair mechanisms.
And then there's rapamycin, right?
Yeah, rapamycin is huge. It functions by inhibiting the MTO pathway.
Yeah.
When MTO are suppressed, the cell registers nutrient scarcity and halts protein synthesis in favor of cellular cleanup. Consistent MTOR inhibition pushes mouse lifespans out by 15 to 20%.
Okay, but here is the friction point I'm seeing. A 20% lifespan extension sounds phenomenal in a controlled lab, but applying an immunosuppressant like rapamycin or a glycemic control drug like metformin, that carries really complex systemic side effects.
It absolutely does.
A 34-year-old father of two who's exposed to whatever pathogens his kids bring home from daycare every week, he can't really afford to have a suppressed immune system or blunted exercise adaptations, right? We have to look at the actual biological timeline of human functionality here.
The timeline is critical. Look, from an evolutionary biology standpoint, peak physical output, maximum bone mineral density, optimal hormones, peak muscle mass, it's all concentrated between ages 15 and 30.
Right.
Between 30 and 50, the body enters a state of gradual functional decline, assuming reasonable maintenance. But the data shows a violent inflection point between 50 and 60.
The health span cliff.
The health span cliff. This is when that cellular trash, the accumulated senescent burden, crosses a critical threshold.
Well.
The localized inflammation becomes systemic. The joint pain becomes chronic. Metabolic syndrome sets in.
But the brutal reality presented in the literature is that at 34, your enemy isn't actually aging yet.
No, it's not.
The fatigue and stiffness you might feel, it's accelerated biological aging driven by lifestyle neglect. And the primary driver of this is the progressive loss of metabolically active tissue. We have to talk about sarcopenia.
We really do. The data here is grim.
It is. Beginning around age 35, an untrained individual loses roughly 1% of their skeletal muscle mass annually. If you do nothing, by 50, you've lost 15%. That's why a 45-year-old feels 55. It's not wrinkles. It's a loss of load-bearing tissue.
And the insidious part isn't just aesthetic, right? It's the physiological mechanism. Muscle is a dynamic endocrine organ. It acts as a primary sink for blood glucose, drastically reducing systemic insulin resistance.
Plus, contracting muscles secrete myokines.
Yeah.
Right.
Exactly. Myokines are these peptides that actively downregulate systemic inflammation. When you lose 15% of your load-bearing tissue, your entire biological infrastructure has to operate at a higher RPM just to execute basic daily functions.
So feeling old is largely just the neurological feedback of a weakened musculoskeletal system struggling against gravity.
Spot on.
Which brings us to the operational protocol. If muscle loss and metabolic decline are making us feel old, how do we actively fight back on a tight schedule? I see an enormous section in the sources dedicated to supplements. You know, NAD plus precursors like NMN, resveratrol. Shouldn't you just take these and call it a day?
Absolutely not.
Right, because taking NMN while sleeping 5 hours and skipping exercise is like putting premium fuel in an engine that hasn't been serviced in a decade. The return is zero.
A fundamental misunderstanding of cellular metabolism. You can flood the system with NMN, but NAD+ requires an active salvage pathway to be utilized effectively. Without the metabolic demand created by physical exertion, supplementing these is just biologically redundant.
Okay, so the literature points to a highly specific, time-efficient biomechanical intervention, the 2-to-1 protocol.
Yes. 2 resistance sessions for every 1 cardio session.
Let's break down the mechanics of the resistance requirement. We aren't talking about, like, bicep curls here.
No isolation movements. We need heavy compound mechanics, squats, deadlifts. The primary goal is mechanotransduction, converting mechanical tension into chemical signals.
Loading the axial skeleton.
Right. It initiates a massive endocrine response. The mechanical tension forces a localized activation of MTOR in the muscle tissue, signaling for immediate protein synthesis while simultaneously stimulating the release of endogenous growth hormone and testosterone.
Which is the only proven mechanism to arrest that 1% annual decline of sarcopenia.
Exactly.
Now, what about the cardio component? The sources split this into 2 distinct energy systems.
First is zone 2 training. Brisk walking, essentially. Prolonged, steady-state output. This is purely about mitochondrial architecture. By spending 45 minutes at this specific intensity, you trigger mitochondrial biogenesis.
You're forcing the cells to build denser, more efficient mitochondrial networks.
Right. If the objective is to sustain a 5-hour hike at altitude with your children at age 55, Zone 2 is the foundational architecture of that capacity.
Okay, and the second cardio system is high-intensity interval training, or HIIT.
Oh.
And the mechanism here is fascinating because it directly impacts the Dunen pace score.
Yes, for those tracking the longevity space, Dunen pace is a highly accurate third-generation epigenetic clock. It measures the real-time speed of biological aging.
Not just estimating chronological age.
Exactly. And clinical trials demonstrate that just 8 weeks of rigorous HII protocols significantly decelerate a person's Dunen pace score. The extreme metabolic stress of HIIT forces rapid mitochondrial turnover. Defective mitochondria are destroyed and replaced, which slows the speed at which your cells accumulate damage.
But this entire physical protocol collapses if you ignore the invisible deficit, right? The nutritional threshold.
Protein intake.
Yep.
As we age, the body requires a higher concentration of amino acids, specifically leucine, to trigger the exact same muscle protein synthesis response as a younger body. At his body weight of 85 kilos, the consensus data establishes a strict floor of 130 to 150 grams of protein daily.
Things like eggs, dal, paneer, chicken. Because if you are inflicting mechanical tension through squats and HIIT, but only consuming, say, 80 grams of protein, your body still demands amino acids for repair.
Oh, and it will find them.
Right. It will literally cannibalize your existing muscle to find them. You're eroding your own biological engine to fuel the recovery, thereby aging yourself faster.
Hitting that macronutrient target is a non-negotiable physiological requirement. However, managing the physical input and output is really only half of the longevity equation.
Right, because parenting brings intense stress. The chronic sleep deprivation, the elevated vigilance. The research shows this physically frays the protective caps on our DNA, our telomeres.
And repairing that cellular damage requires a transition into deep parasympathetic recovery. The most profound anti-aging interventions dictate that cellular regeneration does not happen during exertion.
It happened in the dark.
It happens in the absence of light and digestion. We refer to this as the evening blueprint.
Okay, let's map this chronological sequence out. It begins at 7:30 p.m. with the kitchen closure.
Stopping eating triggers autophagy. Autophagy is a highly conserved cellular recycling program where your body basically acts as a biological street sweeper, degrading misfolded proteins and damaged cells.
Cleaning out the inflammatory zombie cells.
Exactly. But autophagy is highly sensitive to nutrient status. If you are digesting, you remain in an anabolic nutrient-storing state. You aren't repairing.
So by closing the feeding window at 7:30, insulin levels plummet, and the body can activate the recycling plant overnight.
Right. Which transitions us into the critical window between 8 and 9 o'clock, the dopamine drop-off.
And we have to address your specific behavioral patterns here, listener. Once the kids are asleep, the natural inclination is to decompress. The sources mentioned exploring massive open-world RPGs like roaming Skillage or the Commonwealth.
And the environments are spectacular, the dopamine loops are highly refined, but from an endocrinology perspective, playing until midnight is a catastrophic error.
You have to hit quick save and power down by 9 p.m. Why is that so rigid?
It fundamentally breaks your circadian rhythm. The retinal ganglion cells in your eyes are incredibly sensitive to blue light frequencies. When you stare at a monitor radiating blue light, combined with the acute dopamine spikes of in-game achievements, you are forcefully suppressing the release of melatonin.
The brain thinks it's noon.
Exactly. It completely derails the biochemical cascade required for slow-wave sleep.
Okay, so the protocol demands a hard power down by 9, which brings us to the analog shift at 9:15, the cortisol flush.
To transition from a hyperstimulated state into a recovery state, the nervous system requires environmental cues. The source material highlights a specific analog intervention tailored to your interests, using your celestron telescope.
Wait, really? A telescope is an anti-aging tool?
Yes. Stepping outside into the cool air, aligning the telescope, and tracking Jupiter or the Orion Nebula. It sounds purely recreational, but the biological mechanism is profound. Visualizing distant, static objects shifts your visual focal length, which is neurologically linked to a reduction in alertness and anxiety.
Oh, wow.
The darkness, the thermal drop, and that quiet, deliberate focus actively clear circulating cortisol from your bloodstream. The telescope signals to your nervous system that the environmental threat level is 0.
Setting the stage for the final threshold at 10 o'clock p.m., the HGH pulse.
You must be asleep by 10 to catch it. The architecture of human sleep is heavily front-loaded. The deepest phases of slow-wave sleep typically occur between 10 p.m. and 2 a.m. And it is during this phase that the pituitary gland releases its massive natural pulse of human growth hormone.
And growth hormone is the master regenerator. It repairs the micro tears in the muscle, thickens bone density. If you delay sleep until midnight, you permanently truncate that slow wave cycle and miss the biggest pulse of natural restorative hormones your body produces.
You cannot biohack your way out of sleep deprivation.
So this brings the entire paradigm into focus. The longevity interventions that actually move the needle for a 34-year-old, they aren't found in an experimental IV drip. They are embedded in the daily modulation of your epigenetic code.
Your daily habits are the code.
Right. By applying mechanical tension through heavy lifting, clearing lactate through zone 2, forcing mitochondrial turnover via HIIT, eating 140 grams of protein, and hacking your circadian rhythm with a telescope instead of a controller, you are actively slowing your biological clock.
And we must ground this extreme physiological discipline in your core motivation. Why are you doing this? In 2 decades, the metrics of your current physical performance won't matter to your children.
No, they won't remember your bench press record.
Exactly. What they will remember is the 55-year-old dad who had the structural integrity to carry the heavy packs, build the campfire, and navigate the trail alongside them without breaking a sweat. Free of the frailty and chronic pain that society has just sort of normalized, you are literally constructing the biological chassis of that future father right now, cell by cell.
It's profound responsibility.
Yeah.
But it also opens up an entirely new philosophical landscape. I want to leave you with a final thought to mull over, one that extends beyond the immediate biology.
It's a big one.
We have oriented our entire socioeconomic structure around a specific health span trajectory, right? You learn in your 20s, build a career in your 40s, and rapidly decline into retirement in your late 60s. But if this synthesis of epigenetic reprogramming, senolytics, and precision lifestyle architecture succeeds in granting the average person the biological function of a 40-year-old at age 75, how does that entirely upend how we view our lives?
It changes everything.
If you find yourself staring down an extra 20 to 30 years of highly capable, vibrant physiological health, what does a career actually look like? If the biological machine can run flawlessly for a century, how will you choose to navigate the map?